My name is David, and I'm a PhD student at the Weizmann Institute of Science in Israel. And also here is Professor Edith Yerushalmi, my supervisor. And we will talk about designing professional development to empower out-of-field physics teachers. And we will share insights from our program and from Israel. And before I start, I just have to say that it's pretty tough talking to you right now because, as you probably know, the massive terror attack that took place a week ago in my country drew the whole region into a complete turmoil. And just to say that we pray for peace and for a better future for both Israelis and Palestinians. So after saying that, let me introduce the Israeli education system. And it consists of 3 tiers. We have primary education, grades 1 to 6, ages 6 to 12, middle school, and high school. And middle school has less tracking, and students learn in science education, they learn the integrated science course, and they are directed to choose at the end of middle school, they have to choose their elective subjects that they will study extensively in high school. And therefore, in high school, the learning is more tracked, and the goal, or the main goal, is to prepare students for their final matriculation exams. The education system in Israel is highly centralized. The Ministry of Education determines the policy, the curricula, and designs the assessment and the matriculation exams. It also sets the school budgets and employs the teachers. And the final tests are very high stakes. The matriculation certificates and scores determine acceptance into higher education. So it's a high stakes centralized system that we have. I don't know if you know this, but the Israeli economy is science and technology oriented, and therefore there's a high demand for scientists and for engineers. And the government policy is to encourage as much students as we can to choose physics as their high school elective. And the way we try and do it is by tracking already from middle school, creating excellence tracks that specialize in physics and technology for about 30% of middle school students. This is on top of the integrated science course that I was talking about. And with this policy, the school principals really struggle to follow this policy and to meet this requirement, as they have a problem of recruiting teachers. The salaries they can provide teachers that work in a public sector are much lower than those of engineers in the private sector. So the outcome is that principals have to employ out-of-field teachers, and more than 50% of physics teachers in middle school, including these excellence tracks, are out of field. Our system also provides opportunities in the form of professional development and infrastructures that encourage professional development in a way that is built into the education system. One way of doing that is that teachers' salary benefits are aligned with accumulation of PD courses. The PD providers, in this case, it's us and the Weizmann Institute and other institutes, receive public and private funding for designing professional learning and holding professional learning communities. And the PD takes place after school hours, so it's not a burden on school principals. Maybe it is for the teachers, but that's another subject. And in this talk, we will focus on professional development framework for teachers who teach physics in these excellence tracks, and both out-of-field and in-field teachers, as Louis talked in the previous presentation. If we look into the literature that is currently growing in this area of PD for out-of-field teachers, we can see some common pitfalls. First of all, out-of-field teachers participate less in professional development program. Lisa just asked about it, either because policymakers, principals view their situation as temporary, or because they themselves are not motivated to do so. And commonly, these programs focus strongly on content knowledge and some pedagogical aspects. And in many cases, they participate together with the in-field teachers in sort of one-size-fits-all programs. And this, of course, makes them uncomfortable to express themselves, ask questions, and they feel stress and anxiety. Overall, under these conditions, the teachers are in a degraded position as learners. Their prior knowledge and expertise are not valued, and this is a very bad starting point to learn something. We can also learn some design principles from the literature, and we adopt the situated perspective for professional development. It should be anchored in their practice, in their ongoing practice, provide them materials to implement in the classroom already on the next day when they attend our program. And it involves a collaborative reflection on their practice. And we also adopt a constructivist perspective, saying that the prior knowledge of the teachers, the disciplinary knowledge, should be treated as a productive resource. And this talk will focus, and our study focuses on the disciplinary resources that the teachers bring from their original disciplines. And I will talk about this largely. And we try and tailor and design the PD activities so they can serve them, the resources, the practices that they are used to, the knowledge they have from the other field can serve them when they're teaching the new subjects. So putting these principles into practice, we have the Gateway to Physics program. It is actually a network of disciplinary learning communities. We have about 5 communities each year. It's regional communities. And since 2018, we had more than 300 teachers participating. And most of our out-of-field participants do have a background in biology. So they're teaching physics, but they have a background in biology. And as I said, we design our activity to encourage them to draw on their resources. And we do that by several means. We try and anchor our activities in familiar context to the biology teachers. If they can use the particle model, or we do, I'll show some examples after that. And experimental designs, the biology teachers have a strong basis of experimental practices and experimental design. We design activities for dialogic argumentation. We structure opportunities for dialogues between the out-of-field and in-field teachers. And this way they can express and negotiate their perspectives. And we have the participants experience the activities as learners, discuss the pedagogy, underline it, and engage in structured cycles of reflection on practice. They discuss and the dilemmas in their implementation. So I want you to dive into a little bit of an example between physics and biology so you'll understand what I'm talking about. And I apologize for those who are not from the science education community. So the scientific disciplines of biology and physics differ in the phenomena they investigate and the practices they use to investigate and construct scientific knowledge. We know that school biology focuses on complex and many particle systems, and this invites qualitative and descriptive reasoning, whereas in physics, the systems are simplified, 1 or 2 point particles, and this invites quantitative reasoning based on theoretical models, based on mathematical analysis. So, for example, we have our activities. For example, when we talk about falling, we don't talk about free falling, which is a simplified context usually discussed in physics, and that invites this theory-based reasoning. But we talk about falling through air that is more complex, more real life, invites more empirical reasoning, and sort of, as I talked, gives the biology teachers opportunities to bring their strength forward. So I won't talk a lot about research, but I do want to show what kind of research are we conducting in these contexts. So the aim of our studies is to examine how, if at all, our approach serves the teachers. Are they able to build on their former resources? How does their learning process look like? How does this integration between physics and biology look like? And one source of data we have is our documentation and recording of teachers' discourse in the activities. I talked about argumentation that we emphasize. So we use discourse analysis to examine what type of discourse the teachers are engaged in, Specifically, we look for deliberative argumentation, power relations among the teachers, and what epistemic practices, what are they doing? How are they justifying their knowledge, justifying their claims? And do the different teachers, are they able to bring out their different perspective and build on them, as I said. Another source of data we have is teachers report on their classroom activities. We use the boundary crossing framework that was talked about in previous presentations to examine the inquiry activities that the teachers do in the classes. What boundaries do they face, what challenges, and what resources they use that enable the crossing. And I want to show you just two simple examples. This is a chemical garden case. We had a teacher named Delilah, which presented in the meeting one of her classroom activities that is really a nice integration. So she investigated crystal growth. It's a demonstration from the integrated curriculum she's used to teach. It's crystals that grow in water. And it's usually used as a qualitative demonstration. It's three-dimensional, colorful for the wow effect of it. And what she did after our program, while in our program, she tried to mathematically model this growing of the crystal. This was not a simple process. She had to simplify it to a one-dimensional phenomenon, to grow it in a measuring tube, like to give up the three-dimensional colorful effect of the phenomena. But this enabled the quantitative modeling, which is the hallmark, I think, of physics education. And so she brought the familiar resources, her knowledge of the phenomena. We did not, the instructors, I was one of the instructors, we did not know this demonstration. She brought it to us, but she did integrate the PD resources and measured the growth rate. And overall, I think she achieved some type of interdisciplinary inquiry that is even more or higher than what we aim to achieve in physics. A second case I want to show is the bouncing ball case. It's also a teacher that did an inquiry project with her students about a ball bouncing and the dependence of the bouncing height on the air pressure inside the ball. And she did the experiment, which is pretty like standard and with mathematical modeling. But when explaining the findings, she used the particle model knowledge, her knowledge of the particle model to explain why more air pressure means a higher bouncing height. And she integrated sort of the Newton's third law and the particle model in an interesting way. I'll just end with the quote. I'm very proud of this project. I overcame my fears and succeeded in guiding an inquiry projects in physics. I even showed this project to represent the school in the municipal science fair. So we have successes. It's not, of course, only successes. It's a challenging way to go. So I have 1 minute, 2 minutes for discussion. So recently, researchers, and a lot of them are here, have begun to portray effective features for the professional development of out-of-field teachers. And they emphasize the importance of attending to identity issues, motivational issues, providing ongoing support that is uniquely tailored to the needs and the challenges that out-of-field teachers face. Our PD approach joins this effort, and we build on teachers' prior disciplinary resources and practices and provide design guidelines that enable them to integrate these resources into their physics instruction. This approach and overall more positive approach towards out-of-field teaching, I think, requires some flexibility of disciplinary boundaries. It's not truly interdisciplinary, we teach physics, but it requires some flexibility and a more interdisciplinary approach to learning. And in our context, it was biology teachers teaching physics. It's somewhat more easy because they have knowledge and practices that can contribute to physics learning. They have great knowledge of experimental practices. And we want to ask, can this approach be applied to other subjects? We do believe so, provided the differences and connection between the disciplines are mapped and think of, and we offer this as a way of thinking about professional development. So thank you for listening.
Wonderful. Thank you very much, David.